Actually, my system got crashed, so I need to restart it several times. So that's why the delay. Okay, let me just open my presentation. Yes, is my screen visible?
Yes, sir.
Yes, sir.
Okay, so we are talking about the apparatus. So we'll see that. So this is the DC source. This is the multimeter. These are all the apparatus. So how to use a multimeter, that you need to know. And for the DC source also, you can see there are 3 connection in the DC source, right? So plus 1 will give you plus voltage, minus 1 will give you negative voltage, and the middle one is the ground. So if you want, suppose 5 volt positive, you need to connect between the plus 1 and the ground. If you need minus 5 volt, then you need to connect between minus 1 and ground. Now if suppose both settings are at 5 volt and you connect and plus and minus, then it will act as a 10 volt source. Okay, like that. Similarly, you can see the multimeter also here. By using this tool, you can measure several things. You can see the knob. So the knob that you can rotate. So you can see there is some portion for the voltage. There is some portion for the current. There is some portion for the ohm. That means resistance. So if you want to go there, you need to move your knob to the resistance portion. And there you can see there are several division, like you can see it start from 2K, right? 2K, then 20K, then 200K. So that is for the range. Suppose you want to measure a resistance of 195 ohm. So what to do? You should go for the lowest range, because your lowest range is 2 kilo ohm. Now if you go for a very high range, your measurement will come, but that will occur some error because your range is very high. So as per the reading, you need to select your range. Okay. So by moving that knob, you can select your either you want to measure voltage, you can measure everything. You can measure voltage, you can measure current, you can measure frequency, you can measure the ohm, that means the resistance. So how you need to connect the positive and negative port of the multimeter? You can see in the below there are 3 connection. One is common. So the negative connection will be at common. Now you can either choose the 10 ampere one, that is for the current, or other one you can see that is for the either voltage, ohm, that means the resistance, for some other values, other things also you can use that knob. Okay. So now again we need to measure the voltage and current. So if you are coming at lab, we will use this type of instrument. Here also you can see the voltmeter. This is the voltmeter and this is the ammeter. So they are both analog DC. So we can use analog also, we can use digital also. The digital one will give more, you can get reading very easily from the digital one. That is the advantage. Now
Sir,
digital
you are
one is
not audible,
costly.
sir.
Yes. So please mute yourself. So you can see here also there are we can change the range here. From this figure, this is not very clear. Okay, here you can see how we can change the range. This is a ammeter, so we are going to measure current here. Now you can see how to connect this ammeter with the circuit. There is positive and negative connection because this is a DC. So you can see there is a black knob, that is for the negative one, and you can connect the positive one either 1 or 5. So if you are going for 1, then your maximum measurement will give as 1 ampere. If you go to connect to the 5, your maximum measurement can be up to 5 ampere. So you need to have some idea that how much your current should be. If your current is very small, then always go for the one, the knob 1. So what will happen, as your range will become smaller, your reading error will be less. But if you don't know that what our current will be, if you have some idea, then it is okay. If you don't know what our current will be, always go for the higher range. So suppose our current is 0.25 ampere, but we don't know that, so we'll go for very high range. That means for 5. Now when we choose 5 ampere or 5 ampere range, that time if we are want to measure 0.25 ampere, it will come very small. So we'll understand that our current is very small, but it is not measurable by 5 ampere range. So what we'll do then, we'll change the connection then from 5 ampere to 1 ampere and measure. Otherwise, if we just connect to 1 ampere and our current is more than 1 ampere, then this instrument will get destroyed because it is not connected to that time 5 ampere. So if we don't know what is our current, suppose our current is 2 ampere and we directly connect it to ground, that means the black one, and for red one we choose 1 ampere, then it will exceed its range and it will burn. So be careful about that. Okay. So these things are there when we are using a ammeter and voltmeter, and we'll use these apparatuses. Okay. So you will see in the video I'll show right now. There we'll see these things very clearly. Now we'll discuss very quickly because already some time has gone. So everybody knows what is a Norton's theorem. I'll not explain. I'll only explain that what is actually its objective. The Norton's theorem. The objective of the Norton's theorem is any complex DC circuit can be replaced by a current source and a parallel resistance. That is that. So in the figure 1, you can see it's a complex bridge circuit. See this bridge circuit, if we remove the load, that means if we remove the RL, this bridge circuit can be replaced by a current source and a parallel resistance. And that is shown here in figure 3. These two circuits are same in figure 1 and figure 3. Why? You can see the loads are same. Here load is RL, here also load is RL, the same load. And if we remove the load RL, other parts of the circuit are also same. Why? The bridge circuit with the source that is replaced by the current source with the resistance in parallel, that is RN. So this is called, this is our Norton's theorem. What we need to prove here. So through this experiment, we practically try to prove Norton's theorem. Now, if we want to prove that Norton's theorem is valid, that means what? That means the figure shown in, the figure is in figure 2 and figure 1, they are same. That we have to show. Now, how to show that the figures are same? If the figures are same, then if we connect the load, that means the RL, if we connect with the circuit, that time the voltage across RL and current across the RL, if we take the measurement of that, that means if we take the load voltage and load current measurement for figure 1, and if we again take the load current and load voltage measurement for figure 2, and if we plot them, those two graphs will come same. If the load characteristics are same for figure 2 and figure 1, that means if we measure the load voltage and load current, because except the load, other portion of the circuit should be replaced. This circuit should be replaced by this circuit in figure 2, right? So whatever voltage or current will come for figure 2, whatever load voltage or load current will get at across RL, the same amount of load voltage or load current need to be got in case of figure 1 if the circuits are same. Now that means the graph, you can see it is shown in right hand side. That is the graph between the IL and VL. That means that is between the load voltage and load current. So the graph between load voltage and load current for figure 1 and the graph between load voltage and load current in figure 2, they need to be same. If they are same, then we can conclude from that, okay, that means our circuit is same and Norton's theorem is valid. Yes. So up to this, any confusion?
No.
Now the next thing is how to get the graph. So we want to compare these two graphs, right? So how to get these two graphs? So for the first figure, we can see this bridge circuit. So what we'll do, will create this bridge circuit in our experiment lab. You will see how I am creating the bridge circuit. Now once this bridge circuit will be created, the bridge circuit contain what does the bridge circuit contain? There are 4 resistances P, Q, R and S. So they need to be connected in this way that one side of the P will be connected to one side of the Q, one side of the another side of the Q will be connected to the one side of the S, and another side of the S will be connected to the one side of the R, and other side of the R will be connected to the P. Then this configuration will come, and as per this I will make the circuit that I will show the video. But before that, once this circuit is completed, we can connect with that circuit the load, that is our RL. So the load is varying between 0 to 100 ohm. So what we'll do, we'll take the minimum amount value of the load. Suppose we'll start from 5 ohm. We don't know. Maybe we start from 3 ohm also, or maybe 10 ohm also. So, but we'll get actually, if you will see that when I will be doing the experiment, that time you don't know physically that how much portion is what resistance. So we'll try to move very little by little, and we'll start from one end of the load. That means we'll take that is the minimum load resistance value. So we'll start from minimum load resistance value, and at that load resistance value we'll try to measure what is the current flowing through that resistance, load resistance, and what is the voltage across the load resistance. So what we'll be doing, we'll connect with this circuit one ammeter that is will be in series with the load resistance, and one voltmeter that will be in the parallel with the load resistance, and we'll measure the current and voltage value. So we'll get one set of VL and IL. Now next we'll move the RL is a variable resistor, so we'll move the knob. You will see that I will be moving the knob. So what will happen, the RL value will increase than the previous value. So we get another set of VL and IL. Then we'll increase again. We'll get another set of VL and IL. So we'll get different point on this graph. We'll connect those points and we'll get this curve, VL and IL. Okay. So this one we can easily get the load voltage and load current from this circuit. Now we'll come in this circuit. Now practically we are not implementing this circuit. So what we are doing, we are trying to solve this circuit mathematically. Yeah, okay. So if you see this circuit, here we'll get this equation. You can see IL is equal to ISH minus VL by RN. So think about this. If your load voltage is VL, that means voltage across RL is VL, then voltage across RN is also VL. Voltage across ISH also VL, because they are in parallel, right? Now how much current is flowing through RN? That is VL divided by RN. That much current is flowing through RN. So what will be the current? What will be the load current? That is through RL or IL. IL will be equal to total current, that is ISH, minus the current through RN, that is VL by RN. So this equation we can get from this diagram, and we will try to plot this equation. You can see this is the relation between the load voltage and load current, or IL or VL, and this is something like Y is equal to mx plus C, where C is ISH and our M is minus 1 by Rn. So from this equation, we can plot the graph between VL and IL, where we get that our Y interception will be equal to ISH and our slope will be equal to minus 1 by Rn. Here there is a mistake. The slope should be minus 1 by Rn. Okay. Now we have already got two graphs. One graph we have got from the experimental value, and we can plot that. Another graph we are getting from our mathematical equation, and we can plot this graph. Now we have to compare these two graphs. So if we want to compare these two graphs, then what we can compare, if our Y interception and slopes of these two graphs are same, that means the graph, both of the graphs are actually same. So we'll try to see that here for this graph you can see our Y interception is ISH and our slope is minus 1 by Rn. So we'll try to find out that for this graph also our Y interception is ISH or not, and our slope is minus 1 by Rn is not, Rn or not. So for that, what we need to find out? We need to find out ISH and Rn. So what is ISH? if you know what is Norton's theorem, what is ISH, how to measure ISH, we need to short circuit the load, and the load current, that is our ISH. That we can get from Norton's theorem. That how to calculate ISH, we need to short our load, and that load current will be our ISH. So what we will be doing, we will see that I will short the load and I will try to measure the load current. So practically I will make this circuit, and then what I will be doing, I will remove the RL from the circuit practically, and instead of the RL I will connect one wire. So if I connect one wire, that means that portion is short circuited. So C point and A point will be short circuited, right? If we connect a wire, and that wire will be passed through some ammeter, so we'll register the current, the short circuit current. So that will be our ISH. So practically we'll try to measure ISH, and whatever practical value we'll get, we'll try to compare that ISH value with our Y interception from this graph. And if those two interception are equal, then the first condition is okay. Then we'll try to measure our slope of the graph, and we'll try to compare it with Rn, with minus 1 by Rn. Now how to calculate Rn? Rn is equal to, this is very important, Rn is equal to VOC divided by ISH. That means open circuit voltage of the load divided by short circuit current of the load, that is Rn. So what is actually Rn? Rn is the Norton's resistance. It will be equal to R Thevenin, RTH. And you have already done in experiment number 1, right? How to calculate R Thevenin. That time also we are doing the same thing, because Rn and RTH, they are same. So how to calculate Rn? That is VOC divided by ISH. So what is VOC? It is open circuit voltage of the load divided by short circuit current of the load. Now the short circuit current of the load we have already measured. To calculate ISH, what we need to measure? We need to measure the open circuit voltage of the load. That means the load need to be open circuited. So we'll remove RL, and it will be open circuited, and we'll connect a voltmeter across it to measure the open circuit voltage. Now once the open circuit voltage and short circuit current are measured of the load of the same circuit, we can calculate Rn very easily by dividing them. Now we will calculate minus 1 by Rn, and we will try to find out that the slope of this graph is equal to minus 1 by Rn or not. Okay, any confusion?
No, sir.
So if we are going for two things, we are seeing that our Y interception is equal to ISH or not. That is our first condition. Second condition is our slope that we are getting, that is minus 1 by Rn or not. Okay. So if these two conditions satisfied, that means our Norton's theorem is correct and it is experimentally proved. So you'll see that. So you can see this is the procedures. So if you see the procedures are same, I'll just discuss one by one. First, we have to set up the circuit as shown in figure 1. That means the bridge circuit. We can go for either highest value of RL or lowest value of RL, and we can move from there to another value and to get different VL and IL, right? Then what is the second step? Switch on the power supply and set its voltage V in to a convenient value. So our input voltage, that is V in here, need to be fixed. So we'll fix that. Suppose at 10 volt, you will see in the experiment I will fix that it suppose 20 volt. Whatever value we are taking, we have to keep that voltage constant throughout the experiment. Now what is number 3? By ammeter and voltmeter, we'll measure the load current and load voltage. Then what is our step number 4? We either we gradually increase or decrease RL value, and for each RL value we'll repeat step 3. That means we have to measure VL and IL, keeping V in constant. So V is in constant for the total experiment. So we have to change the RL value, and accordingly we will measure the VL and IL. Now number 5, plot IL versus VL graph and find the interception, Y interception, that is ILO, Y interception, and slope M from that graph. Then again we'll take the millimeter reading you can see step number 6. Ammeter reading when load terminals are short circuited. That means you will see, we'll connect that by a wire and we'll measure the current. So that will give your ISH. Okay. And how to measure RN? That is VOC divided by ISH. So for that, we'll do open circuit of the load and we'll measure the voltage. Then already the short circuit current has been measured. We can calculate RN, right? Now once RN and ISH is calculated, we have to compare it with ILO is equal to ISH or not. That means the y-axis intersection of the graph, that is equal to the short circuit current of the load or not. Or and M is equal to -1 by Rn or not. If it is coming, that means this verifies Norton's theorem. Yes, any confusion?
Yes, sir. So one thing,
Yes.
sir, will we mention the procedure in our lab experiment? Because procedure.
No. In lab experiment, whatever there is given, a document has been produced, right? So where we will find out each experiment.
Yes, sir. Yes,
So
sir.
everything presented there, you need to be right except the procedure. Okay.
Okay. Thank you, sir.
But circuit diagrams you have to show. If some diagrams is there inside the procedure, that you need to show and explain. But procedure, no need to write. Except procedure, you have to write every other things. Okay.
Sir, if earlierly if somebody written procedure, is it acceptable or
Yes,
must
it
be?
is acceptable. It is acceptable. No problem. No problem. If you have already written procedure, that is okay. But there is no need. Okay. Yeah. Okay, we'll discuss this later. Let's concentrate on the experiment. Okay. So these are the some tables, so that we'll see how we are getting. So what are inside the table? There are load resistances, load value, so load resistance value, load voltage and load current. Okay, so we'll see this. So how to calculate? So when we are doing the experiment, you will see that I am measuring only load voltage and load current. So how to calculate load resistance? Just divide the load voltage by load current. You will get the load resistance, right? So we'll measure the load voltage and load current. From there we'll form the graph and we'll take the open circuit voltage and short circuit current. From there we'll measure RN and finally we'll compare ISC here or ISH with the y interception, and with Rn -1 by Rn will be the slope. Okay, so that we'll see. Now what we need to measure? We need to measure VL. We need to measure IL with different RL position. And finally, after that, we need to measure VOC, open circuit voltage of the load, and ISC, short circuit current of the load. Okay. So let me play. So this is the apparatus one. So first I will explaining the apparatus. Just 1 second. Let me. Okay, so it is visible.
Yes, sir.
Yes, sir.
Today we are going to do experiment number 2, which is exactly network theorem. This is for Norton theorem and maximum power transfer theorem. So we will first see what are the apparatus. So if you want to find out in this experiment, first we need a voltage source. So this is the DC voltage source, and this has a separate connection. This black one, this connection. So see, first have to give the connection. Then we have to give the supply. Now this DC voltage can go up to 30 volt. So to increase the voltage, you can just place here, and you can see the voltage is now 20. If you want to increase more, it is 30. Suppose we want to decrease, again we have to click like this, and 20. Suppose we have to go to 25, then we have to click again like this, and then we can increase like this, 22, 23, 24, 24. So this is the voltage source, and if you can see that there are three connections. The middle one is the ground one. So you connect to the positive one and the negative one. So the red one is positive, black one is the negative. From here, where will be connected. Now here we can see there are four resistances. Each resistance have 20 ohm value. So we have to make the Wheatstone bridge, the bridge circuit. So that this circuit will be made by these four resistances. And there are we need one voltmeter and ammeter, and this is the digital voltmeter, and this is the digital ammeter. You can see here V is written, that means voltmeter, and here A is written, that means ammeter. Now this ammeter is rated up to 1 ampere. We can measure the current up to 1 ampere here, and for this voltmeter we can measure up to 50 volt, and our source is of 30 volt. So this voltmeter and this ammeter is okay for our experiment. Now about this load, here we can see this is the resistive load. Now the load need to be variable. This is up to 100 ohm, and we can vary this load by varying this thing. So by varying this one, we can increase and decrease the total load value. So this is our total setup, and we will connect everything by this type of wire. Where you can see it has hooks like this. So this is for easier connection. So we can just put the wire like this, and this is our connection. So up to this is our total apparatus. Okay, so after this we'll see the connection. So how to make the connection. So this is the total diagram that we have to make. You can see there are four resistances P, Q, R and S, and the resistance are connect side by side, and with that one ammeter is connected, source is connected, load is connected, and a voltmeter is connected across the load too. So this ammeter and voltmeter are connected to get load voltage and load current. Okay. Now we have to see how we can easily connect. So resistance we can easily connect if we take some positive and negative of the resistance. So we know that basically this is a DC circuit, so there is no positive or negative things, but it will be easier for us if we can connect the resistance with some positive and negative. So suppose we'll take that this is positive side of P, and this is negative side of P. Similarly, this is positive and negative of Q, this is positive and negative of S, and this is positive and negative of R. Now you can see here how the circuit is connected. The negative of P is connected to the positive of Q. The negative of Q is connected to the positive of S. The negative of S is connected to the positive of R, and negative of R is connected to the positive of P. Now if we see in here there are four resistances. So suppose this is P, this is Q, this is R, and this is S. Now you can see each resistance has two sides again. Here also we are taking the same thing. So the red connections, they are positive. The black one, they are negative. So we start to do the connection. Okay. So let me start the connection. So you can see this type of wire is there. So by which we can connect very easily. So first connection we see here. The connection is from negative P negative to Q positive. So this is our P, this is our Q. So P negative means this black one. So we'll connect to this black one very easily, and it will be connected to Q positive. So this is Q positive, the red one. So this connection is done. Then we come here again. We can see Q negative will be connected to S positive, right? This is Q negative. So this is PQRS. So Q negative will be connected to S positive. That means this one. Now this connection is done. Now S negative will be connected to R positive, right? So this is S negative. PQR, so it will be connected to R positive. That means the red one. Yes. Now the last one, that is R negative, will be connected to P positive. So you can see that this is our R negative. This will be connected to P positive. Now our this circuit is completed. Now from here we can see this B. If we try to see the B point, the B point is the connection point of P negative and Q positive, where the positive of the voltage source is connected. So we can connect either in P negative or Q positive, and we can connect the voltage source, right? So we'll do that. We'll take the positive of the voltage source, so this one, and this will be connected to here. That means either P negative or Q positive. So we have P, Q, RS. So we'll connect it to Q positive. That is same as P negative. So this portion is done. Then again we can say about D point, where we can connect R positive or S negative, and this D point is connected to the negative of the voltage source. So we'll see that this is the negative of the voltage source, and it will be connected to D point, which is positive of R. So PQR. So this is the R positive. So here this connection is, so the source is connected. Now we have to connect the load, but the load is connected through a ammeter. You can see, and the ammeter is connected to C point, but C point is either Q negative or S positive. So this C point will go to the ammeter. So we'll take some other wire, where this C point, that means Q negative. So this is Q negative. See, so this Q negative will go to the ammeter, and if we see here again, the another end of the ammeter will be connected to the load, right? So we'll take another wire, and this is the another end of the ammeter, which will be connected to the load. Yes. Now, if we see here, this connection is done, then this load end connection will go to A point, which is P positive, P positive of P or negative of R. So we'll take another wire. Okay, we have to go for a bigger wire, where the P positive, that means this is P, this is the positive of P, so this is the P positive. So this will be connected to another end of the rheostat, that is here. So our total connection is done. Here if we see, only the voltmeter remains. The voltmeter is parallel to the load. So this voltmeter can be connected to M point and M point. So M point is the positive side of the ammeter. So we'll take another wire, where this point is the M point, that is the positive of the ammeter. So this point will be connected to the voltmeter. And if we see here, another end of the voltmeter will be connected to the load, to the end point, which is exactly the same as the A point. So we'll connect the voltmeter, another end of the voltmeter, to A point. So we'll take another wire. So if we see A point, that is positive of P. So this voltmeter will be connected to the positive of the P. That means this point. This is the positive of the P, right? So now if we can see here, our total bridge circuit is completed. With that, our source is connected. With that, the ammeter is connected, the load is connected, and the voltage voltmeter is also connected. So our circuit is completed. Okay. So any confusion up to this?
No, sir.
Yes.
No,
Okay.
sir.
No, sir.
Okay. So as our connection is already done, we'll see how to take the reading by varying the load resistance. So the load resistance you have already seen. There is a knob. So you can move that knob, and by moving that knob, you can vary the resistance. Okay. So you'll see that. Now as the circuit is completed, now we'll start to take the readings. Okay. So for that, first we have to give the supply to the voltage source and supply to the cable. Now it can be seen there is one fuse, so it need to be on. Now you can see all voltmeter and meters are on. Now for this voltage source, the switch has been given, so we have to on it like this. Now for the main thing is for this total experiment, the input voltage that need to be fixed. So here we have tried to give near about 20 volts. You can see it is 19.5 volt, but it is fixed. It is fixed for the total experiment. Now, if we come to this table, here we can see what we have to take. For suppose 4-5 reading will take, and for each reading we have to take load voltage, that is VL, unit is volt, load current, that is IL, unit is ampere, and what is our load resistance. That this one we need to calculate. How? This is we know very easily, that is VL divided by IL. That will be equal to RL. So we need to take VL and IL value. From there we will calculating the RL. So we'll see first. This is our total. This is our total setup. So this is our load. So what we are going to do? We are trying to vary this load, and accordingly the load voltage and load current will be varied. Now you can see this is our ammeter, which will give the load current value, and for here this is our voltmeter, which is giving the load voltage value. So the first reading we can take from here, we can see it is showing near about 0.3, near about 0.3 volt, and our current value is showing 0.17 ampere. So our first reading, that will be, this is 0.17 ampere, and the voltmeter reading, that is 0.03 volt. So this is our first reading. Now to take the second reading, we need to shift a little bit our resistance. So suppose up to this. So here we have changed our load, and we'll see that our current and voltage also will change. This current reading is now 0.11, and if we see the voltage reading, it is now 1.6 or 1.7. So it will vary a little bit because there is electrical voltage fluctuation. So it will be 0.16 and 0.11. So accordingly we'll give the second reading, that this one is 0.11, and our voltage reading, that is coming near about 1.6. Now we'll try to vary this one a little bit more. So suppose like this. So here we'll see this is our current rating. This is our ampere reading, that is 0.07. So this is 0.07, and if you see the voltage reading, now this is coming 2.4 volt, 2.4 volt or 2.5 volt. So we'll write this as 2.4. Now we'll take another reading like this, and we can see now our current is 0.05 ampere, and if you see our voltage, now our voltage is 3 volt, near about 3 volt. So we'll write down that. So this will be 3 volt, and this is 0. We'll take another reading. So like this. So here we can see our current is now 0.04 ampere. So this is 0.04 ampere, and if we see our voltage reading, it is near about 3.3. So our voltage reading will be here, it will be 3.3, and the last reading we will take here with the maximum value of this rheostat like this, where the current reading we can see it is 0.03, and for the voltage reading you can see it is near about 3.5. So we'll write that this is to be value will be equal to 3.5. So we can see a trend, like, so the current is decreasing and the voltage is increasing with each reading. Now we can easily calculate RL for each reading by doing VL by IL, and we can complete this table. So this is the first set of reading. Now once this VL and IL we have already got, by that we can plot this graph, right?
Sir, in the taking of voltage, is that 0.16, 0.24 or 2.4 like that, sir? Is the point before 2 or after 2?
It is 2.4. Okay, like 3 it maximum goes up to 3.4 volt in that experiment. Okay,
Okay, sir. Okay.
yeah. So we have already got this graph. Now we can put these VL and IL values here and we'll get this straight line. Now what to do? We'll increase this straight line up to y-axis and we'll get the ISH. And slope we can easily calculate by dividing x by y. So that we will see. So once we get the y-interception and slope, we need to calculate ISH and RN. So for that, we need to calculate the short circuit current and open circuit voltage. Okay, so we'll see that. So first we'll see the open circuit voltage one. So now we have to go for our second table. So one thing we know that we need to calculate the internal resistance of the total bridge circuit or Norton resistance. So that formula of that is VOC by ISH. So VOC is the open circuit voltage of the load. ISH is the short circuit current of the load. So we'll see, first we try to measure VOC. So to measure VOC, this circuit is done. So you can see here the load is removed and the load is now open circuited, and to measure the open circuit voltage, a voltmeter is connected. So here this that circuit is previously done. So we have removed the load and we have connected the voltmeter here. This voltmeter is connected like this circuit. Now we'll have to maintain our voltage, source voltage same. So our source voltage is almost same. And we have to keep this source voltage same. By keeping this, we have to measure this voltage, and if we see what is the value of this voltage is varying between 4.2, 4.1, sometimes 4.3. So we'll take a mean of it 4.2. So we will know that our VOC that will become 4.2 volt. So now next thing, VOC is already calculated. We have to calculate ISH. ISH is we have to short circuit the load, and accordingly we have to take the ammeter reading. So this is a circuit to measure ISH. You can see the load is now shorted by a ammeter, and the ammeter is connected to take the short circuit current. So the voltage source will have to keep the same voltage. So we'll have to, this is deflected little bit. Yes, so this is now okay. So we have to keep the same voltage, and the ammeter is connected here. So the ammeter reading will get, it is 0.19. So obviously our ISH value, that is coming 0.19 ammeter. So up to this it is done. So the short circuit current value is coming 0.19 ammeter. Now the thing is, when we have calculated ISH and RN, then we can compare. And we can go for our last step. Here you can see step number 7. We have to see that ILO, that is the interception of y-axis, will be equal to ISH or not, or OAM equal to minus 1 by RN or not. If these two will not be exactly equal, why they will not be exactly equal? Because we have seen there was voltage flicker, voltage was changing sometime the input voltage, DC voltage, that is also little bit varying.
Sir,
This
loose
is
connection
the,
can state.
yes,
Due to loose connection, some
yeah,
error is.
the loose connection is not there, because if there is some loose connection, then you will get no current. So you will not tell about loose connection, but instead of, you can talk about some faulty connection. So somewhere may be a little bit faulty, so their resistance may change. So if we connect a wire for short circuit, that means that wire also have some resistances, so that is not actually short circuited. So there is these problems for practical. Okay, so as you are engineers, in future we will be doing the practical things. That time you will find out the basic difference between theory and practical. So in theory, everything is seems easier, but when you are achieving that in some practical values, things will be different. So that's why these will not be exactly same, but you will understand that they are almost same. So that means that will verify Norton's theorem. Yes, up to this, any confusion?
No, sir.
Yeah,
No, sir.
let me just go for the then next one is very easy. So we have to complete this one also, that is maximum power transfer theorem, and we know what is maximum power transfer theorem. So maximum power will be transferred if our load resistance will be equal to our internal resistance,
resistance.
that is R Thevenin on Rn. So we know how to calculate Rn, right? It is VOC by ISH, and we have already calculated Rn for the bridge circuit, that we have already calculated Rn. Okay. Now what we need to do, we'll again connect a variable load. You can see RL is connected to the same circuit, same bridge circuit. Will connected RL, and we'll again vary the RL, and we'll take different VL and IL value. Now, just like the previous one, just like the reading. So that's why I'm not showing the video of the reading, because in the same manner, we have to take different VL and IL for different value of RL. Now, once that VL and IL has been taken, you have seen that we have taken 6 sets, right? So for those 6 sets, we can calculate the power, right? Just multiplying VL and IL, we'll get the power. Now, for those 6 cases, we have got the power. We know what is the RL value for each cases. Just dividing the load voltage with load current, we'll get the RL. And in the table also, there is some RL, right? So we can plot the graph here. So you have to plot another graph, that is between P and RL. Now once we plot this graph, you will find out the maximum amount of P where that is occurring. We'll draw a perpendicular on that resistance axis, and we'll get the value of RO here. Finally, we have to compare that RO is equal to RN or not. So if RO is equal to Rn, that means our maximum power transfer theorem exists. If not, that means it is wrong. And you will find out that RO will be equal to Rn. Not exactly, but it will come very close. So that's why for this, I am not showing any reading, because the reading that you have taken for the previous experiment, that is sufficient for this one. Only you have to know how to calculate the power, that is, it is a DC circuit. So just multiplying the voltage, load voltage into load current, you will get the load power, and that you need to plot. Okay. So here procedure you can see again same. So we have to set up the circuit, we have to switch on the power supply, we have to insert the load resistance, and we have to increase or decrease the load resistance from minimum to maximum value, and for everything we have to measure VL and IL. Now once we have measured VL IL, we can calculate RL, you can calculate PL, that means the load power. Now once load power is calculated, we have to go for step number 6, plot P versus RL, and from the graph find the values of RL at which power is maximum. So at maximum P you have to draw a perpendicular, and this value will be equal to, here it is given as RO, so RO should be equal to Rn, which will verify the maximum power transfer theorem. And what is the value of Rn? That we have already calculated for Norton's theorem, right? So this is the table, this you need to complete. Again the same table you can see IL, VL, RL, that we have already done. So with this table you can do this experiment. So that is over up to this. So any confusion regarding this?
Sir, one thing, sir, while plotting the curve, plotting the straight line, sir, many points are there which is not coming in the straight line. So, sir, what we'll do for that?
Yes,
We'll
so
draw.
that is the difference. So that means what you need to do. You need to do some assumption. So you have to think about that which straight line will be closest to all of this point. According to that, you have to draw the straight line. There that will be a straight line. It is not like that it is a curvature. It will be a straight line, and you have to ignore some readings also. Okay, if you have to ignore some reading, that is also okay, but you have to connect most of the readings in that graph. Okay.
Okay, sir.
Yeah. So there will be some difference between the theory and the practical, and that you have to explain also in your report, that why it is not coming, why all the points are not coming under the straight line. Why? Because you have seen that into that much time. So I was doing the experiment into that much time of there was voltage flicker. The load voltage was changing. Sometimes it was 3.5, sometimes it was 3.3, sometimes in between 3.3 and 3.5. So similarly, the current also will change. The input voltage also will change. And why it is changing? Because the supply that we are getting from the grid, that is not exactly 230 volt. Sometimes it is 231 volt. Sometimes it is 229 volt. So as our supply is not exactly fixed, so this will also vary. Okay. Yes. Any more
Sir,
confusion?
one thing, can we say that fault in a reading is also due to some kind of internal resistance in ammeter and voltmeter that is there? It is not ideal ammeter voltmeter which we are
Yes,
using
so
for.
those things are there. The source, that is also not ideal, right? If it is a voltage, ideal voltage source, the resistance need to be zero. But that is not possible for a practical case, because if there is some wire, the wire will have some resistances. So those things you have to mention. You have to think about and you have to mention. Okay. Yes. Anything else regarding this experiment? Now next I'll tell how to write the experiment. Up to this, any confusion?
No, sir.
Okay. Okay, let me find out this one. Yes, so this is experiment number 2. First you need to write title, then objective, then the circuit diagram, then here theory. Theory also you have to mention. Procedure no need to write. There will be 3 circuit diagrams, right? One will be the bigger one, this one. Another one when the load is short circuited, like this one. Another one when the load is open circuited, this one. You have to complete the apparatus use table, then will come to experimental result. So in this here you have to write table 1. So table 1 you can see load resistance, load voltage, load current. These three is measured first, then open circuit voltage, short circuit current and RN. This is also calculated. So table 1 you can complete. Then table 2, determination of the slope and intersection of ILVL straight line. This will come from your graph, that you graph you have drawn. From there you have to complete this table number 2. Now we'll come to table number 3, where we'll compare that ILO is how much, that will come from the graph, M that will come from the curve, IN that will come from the first table, that is IN, or this is ISH, okay, short circuit current or Norton current, IN. So IN and ILO will be exact matching. It will not be exact matching, but it will come very closer. Then we'll see what is our this is RS has been written, but instead of that we'll put here RN or Norton resistance, and from there we'll find out what is our slope, that is -1 by RN, and we'll just try to compare that with the M value, okay, in the second column. So and another one, remarks. So what you got from this table? If it is matching, then why it is matching? If it is not matching, you have to write it is why it is not matching. And if it's not exactly matching, that time also you have to mention why it is not exactly matching. Okay. Similarly, for this one also, theory you have to write down. Procedure no need to write. Theory and circuit diagram. So circuit diagram already has been given for Norton's one. So for this, no need of any circuit diagram. You just write theory, then apparatus used, whatever apparatus you are using. Then this table, first table. So load voltage increasing, decreasing. Will take any one of them. You can take both of them also. So in our practical experiment, whatever video I am showing, there I was increasing. So we'll take the only increasing one. Again here how we are calculating power. Here we are calculating power by V square by R. And in our experiment, how we are calculating by V into I. So here it has been shown that why we are going for V square by R, because no need to measure the current. But for the previous experiment, we have already measured current. So we can use that. So no need to use V square by R. Instead of that, we can use just V into I. So VL into IL, we can measure power. So once we can measure power, we know RL, we can plot that curve. So verification of the next table, we will see what is our RO. That is RO, or this is actually RN or R Thevenin, the first one. Okay. So what is the internal resistance of the circuit that you have to mention. Then from the graph, you will find out what is the in the y-axis, what is your resistance where the maximum power is obtained, that you have to write in the second one. And third one, you have to write your remarks that it is matching or not, why it is matching and why it is not matching. Okay. And then you have to write your comments. So what you have learned from the experiment, that you have to write. Yes, any confusion? Yes, anything?
Sir, why do I have to submit these experiments?
That we have already mailed, right? Where you need to submit?
No, sir. The date is not
No,
intimated.
sir.
It is not mentioned.
Yes, sir. That date is not mentioned in the mail. The
Date is not
procedure.
mentioned, but the assignment is given or not.
Yes, sir. It is
Yes.
given, sir.
Yes, the
So,
assignment is given, but the submission date is not mentioned.
so it will be inside this week. I think it will be by next Sunday. That date will know you by this week. But once you complete, you submit it. Okay. So it will be, I think today is 7th. So I think maximum will give time up to next Sunday. That means up to 13th. So I think in between 13th you have to submit. And in between this week we'll take the Viva also. Okay.
Sir, in
So
this week means after 13 or before 13, sir?
before 13. All your 8 experiment is over. Yes.
Yes, sir.
So by this week I think we'll have to take the Viva. Actually there is some faculty holiday in the next week. So that's why we cannot shift our exam there. And after that your exam will start from 21. So before that we have to take the Viva, right? So there is only one spot that is in between this week. So the respective teachers or respective faculties will be contacted you, the respective section, and as per his or her instruction, the exam will be, that section will be conducted, and the time, what will be the, how much weightage, that everything is depend upon him. Okay. So I think I have, for me I think I have J section, so that I have to check again, but I can tell thing for only J section. So for other section, suppose here is I section also. So for I section, I don't know who is the respective faculty, so you'll get it in your routine, class routine. You will see there who is the respective faculty, and accordingly you have to contact him, or he will be contacted only. Okay, he or she will contact you and tell you about the this lab 5 examination. Yes, any confusion? If there is no confusion, then we'll end this meeting.
Sir, one last doubt. So out of
Okay,
eight,
okay. Let me
why
let
is
me
on eight
let me
experiment, right? Sir?
let me do this first. Let me stop recording. Yes.